quantify, we could measure. You guys done measuring the dolphins? We're at volume here. Oh, I need to go back to PC. Oh, we do have some volume. Good.
Engineers that understand science. So there's a colleague of mine. He likes to say that scientists ask the question why, while engineers ask the question why not. And what he's getting at here is the fact that the scientist spends his day observing phenomenon, trying to understand what made that phenomenon occur, whereas the engineer spends his day imagining a phenomenon and trying to imagine how to make that phenomenon occur. And I can tell you that you will never be a great engineer unless you understand the science, at least as well as the best scientists do. For more haikus, for a little bit of breakfast with Ted, you can subscribe to this YouTube channel. I'll see you later.
All right, so I'd say that engineers are measuring because they want to control something, because they want to understand that process, because they don't want to ship crap to their customers, right? That's why engineers are measuring stuff. Scientists are measuring stuff because they want to understand something. They have a sort of a theory. They have this idea that they want to know something, and they're measuring now in order to prove or disprove their idea, right? Anybody ever done an experiment and it didn't give you the result you wanted? What do you do when you try to measure something and you say this should be 5, and I measure it and it comes out to 6.5? What do you do immediately when you believe that it should have been 5 before you started that measurement? You measure it again, right? And what do you keep doing? Keep measuring it until you find it's 5, right? Or you've got enough 6.5 answers that you realize that your assumption was wrong. Now, on the other hand, what do you do when you measure something, you think it's going to be 5 and it's 5? Woohoo! Victory dance, right? Done. I'm not sure that's good science. Before you do the science, you should say, I'm going to measure this 12 times. And then measure it 12 times. Rather than measure it once if it's the answer you want, and keep measuring if it's not the answer. So what's the assumption when it wasn't the answer that I wanted, or that I believed it was going to be before I started? What's my assumption? Yeah, go ahead. So our assumption at that point is that something in our process was faulty, right? So we make the assumption that we made a mistake, and that's why the measurement was wrong. What's our assumption when it measures the exact same thing that we thought it was going to? They were good. Our assumption at that point is that we didn't make any mistakes. It was what we thought it was going to be. It was what it was. So in the class, we say we're going to talk about manufacturing science and manufacturing engineering, right? So what do you think? What do you suppose the difference between manufacturing science and manufacturing engineering is? So up till now in the class, we've pretty much been talking about manufacturing engineering, right? What would manufacturing science be? Back here, wait, Aiden.
Manufacturing science would be checking something, checking a distance or measuring something to not necessarily confirm it, but to clarify it.
To clarify it, to confirm it. Okay. So what does science give us in general? Any kind of science, all the hard sciences. Why do we do science? Michael? All right, so it kind of gives you a limit. So what scientists in general are, and so I always, people ask me what I do or who I am or what it is, and I say, well, I'm a scientist and an engineer. So I'm not a scientist or an engineer. I'm a scientist and an engineer as I do this, because sometimes I'm trying to expand the body of human knowledge. I'm trying to help us as humanity understand more than we understood before. That's what I'm doing science. I'm trying to develop fundamental principles, develop rules that explain actions. Right, so we've got what the Newton's laws of motion, right? Was Newton that did the laws of motion? Yeah. What are the laws of motion? Somebody shout them out. Do we know this, right? Chomps. Right, so a body moving in a straight line will keep moving unless a force is applied to it. What's the other one? Edward.
If a force acts, if body A exerts a force on body B, then body B will exert a force that is
Right, equal opposite forces, right? So if I push on something, it pushes back on me. You had something? F equals ma. Force equals mass times acceleration. We like force equals mass times acceleration, right? In fact, I don't think we're going to do anything in this class that you couldn't probably derive as long as you understood F equals ma and you were good at observation. We'll skip some of the steps, so we won't make it derive all the equations as we go through the class. But so F equals ma, and actions, reactions, all that stuff. So that's what we do as science. So as a manufacturing scientist, so a physicist is studying stuff like that, right? As physicists, we like to drop stuff and see how long it takes to get to the ground. There's a funny joke. There's a task. Determine the height of the building. Right? Anybody seen this? It's like a cartoon. I went around the internet a while ago. So it's determine the height of the building. So the scientist, what's the scientist do? Climb up to the top of the building, bring something, get a stopwatch, count how long it takes to get to the ground. You can calculate how tall the building is, right? What's the engineer do? Oh, wait, the mathematician. There's a mathematician in the group too. What's the mathematician do? He did trig, right? He took something, he knew how tall it was, put it next to the building, stood back like that and said 1, 2, 3. Anybody ever measure a building that way? Right? And you can do the math, right? You can figure out how tall it is with trig. What's the engineer do? Excuse me, doorman? How tall is this building? Somebody already knows the answer, right? Why create the answer if somebody doesn't? If somebody already knows it? All right. So engineers are trying to figure things out. Scientists, so manufacturing science. What are we going to study in manufacturing science? Principles of manufacturing. What kind of things do you think might be principles of manufacturing?
Which techniques work better than others?
Which techniques for?
Manufacturing, or
Okay, all right. So we could use science to better understand lean manufacturing. So we said lean manufacturing was kind of a management tool, right? I mean, it helps us manufacture. It helps our manufacturing companies succeed. But it's kind of a management tool, right? So we could use science to study a management tool. So what kind of things would you do if you wanted to do a scientific experiment to study some principle of lean manufacturing? You could go ahead, or if somebody else want to jump in, go ahead.
you could check how many parts were produced per hour, or check the efficiency.
Right. So if we're trying to increase throughput on the part, we could see how many parts were made per hour. We could change something about the system. Right. I think I told you about a study that they did where they were watching this factory trying to get the throughput, right? And so they brightened the factory. They turned up the lights. Right. They got brighter lights in there, and everybody worked faster. They're like, sweet. Bright lights means faster throughput. And then what they do, well, some of the lights went out. I don't know how they arranged this experiment. They dimmed the lights. Everything went faster when they dimmed the lights. Anyway, so we brighten the lights, everything goes faster. Because scientists got this problem. We can observe data points, right? Once we get observed data points, once we get a collection of data points, what do we like to do? Who's seen the movie Office Space? We need to jump to conclusions, right? If you haven't seen the movie Office Space, you gotta see the movie Office Space. I just make that a homework assignment. So we like to have conclusions. There's so we get our data, so we can observe a phenomenon, and we can see what happens. We have to be careful when we start arguing causality. What they finally figured out, because they did a whole bunch of adjustments there, they finally figured out that people worked faster when they thought somebody was watching them. And so when you change the lights, they think somebody's watching. When you dim the lights, they think somebody's watching. So that particular instance. So we can study lean manufacturing with science. What about machining? What about machining could we study with science? Zeb?
The optimal rate at which to rotate a tool, balancing speed against efficiency and how long the tool lasts.
Sure. So we could try to optimize a cutting operation. We could try to optimize a cutting operation. So what are the things that you're adjusting in your experiment that you explain? What are the so the experiment Zeb explained. So did you guys hear that? He wants to optimize the cutting of something by balancing the speed, the feed, what were the other things?
Against efficiency
Against
and
some sort of
lifetime
efficiency
the lifetime of the tool.
and the life of the tool. So what are the things that's varying there? We're building it. We're putting our scientist hat on.
So materials that are being cut.
So we could vary the materials that are being cut. We vary the materials being cut.
The tool size.
We could vary the tool size. Right, what else?
Speed and feed.
Speed. If you wanted to optimize tool life, is that what it was?
Yeah.
I mean, that's an idea. It could be any number of things, but and so these are things that we're varying, right? What are all the things that we're varying? They're all process variables, right? These are all PVs. The thing that we're trying to understand is tool life over here. So tool life doesn't fit into our matrix of CN, FR, DP, PV, right? It's not one of those things. But why is tool life important? Travis.
Because over a while, the tool is constantly.
It could certainly, so understanding our tool life could certainly impact the profits of our company. Yes, Ed?
Also, if the tool has a serious risk of shattering.
Oh, yeah. What happens when the tool explodes? Yeah, back in the day, that's what we did. I do some work with this company that makes capital equipment. So capital equipment is like making a machine. Capital equipment is like machine tools. So this company makes machine tools, and they've been in business since the early 1900s. And they also repair their own machine tools, or rehab them, refurbish them, add new automated controls on them, and stuff like that. And they have a real problem because a machine that they sold in 1930 is still a really good machine. But back in 1930, some guy loses an arm, you go get another guy. So when they bring one in and they rehab it, they have to add all the modern guarding around the 1930s machine. So it's glad you brought that up. So when the tool explodes, it could be bad. So we want to monitor tool life both for profitability and for safety. Yeah.
Another one is if the tool becomes dull, it can affect the product.
So when the tool becomes dull, it will change the DPs that it is creating on the part, right? It will change the quality of the part. So that's another reason we'd like to understand our tool life, maximize our tool life. So we could do a high-level experiment here. what else can we understand about a machining process? What if we really want to, so what's one thing that we want to do if we're going to do this experiment, by the way? One super important thing, we're going to design an experiment where we're varying materials, varying tools, varying speed, varying feed, and see how those things impact tool life. What do we absolutely want to do? Michael? We need some sort of a control, or at least we want to vary them one at a time. Right? So good experimental design would actually keep all those things fixed and vary that one and see how the material impacts the tool life. Then once we get a good feeling for how the material impacts the tool life, we'll keep this one fixed and we'll change the speed, or we'll change the feed and see how that impacts. So that's just, so these are all things that we can vary, the process variables and things that we can vary. So when we're doing an experiment in science, we call this the dependent variable. This is the independent variable. You guys all done measuring the dowel pins? If you guys are all done measuring the dowel pins, pass the calipers and the dowel pins this way and forward, and the cards that way and forward. And when it gets down here, grab one of the calipers. Good, measure it. Okay, so we've got our tool life, vary materials being done. All right, so this is some engineering, manufacturing science that we can do. What else could we science in manufacturing? Yeah.
The design of the machine itself.
So we can look at the design of the machine itself. And you can see the stiffness of the machines. There's actually a professor here at WPI that did all his graduate work looking at the stiffness of machines. Machine tools with poured concrete bases as opposed to cast iron, because he was seeing if the poured concrete would be stiffer than the cast iron. So things like that. So you can do those kinds of science experiments. What if I want to understand, so if I really want to understand, and actually this is a great example, this tool life versus our feed speed, depth of cut kind of thing. So I said our four key parameters that we're looking at are feed speed, depth of cut, width of cut, right? So if I want to really understand those, the reason those are the four key parameters is because people back in the day did a bunch of science, and they determined that those four key parameters had the biggest impact on the speed at which we could cut metal. They did most of this research in the 1930s and 40s, and why did they care about how fast they could cut metal in the 1930s and 40s? Xavier. Yeah, World War II. They wanted to be able to build bombers. They wanted to be able to build ships faster than the other guy, because a lot of times in those kind of battles, it's the guy who can bring more guns to the battlefield that wins, right? So the faster you can build them, the better off you're going to do. So they did a lot of research on that. Feed speed, depth of cut. What they found that was really important to them is they wanted to understand, how long have you guys been looking at that? There we go. I thought you were looking at this. Every now and then I should look at that. So what they wanted to understand was, so if I get my cutting tool here, and I got my, so what makes what cuts? What cuts in manufacturing, in machining? Right. So we've got a cutting tool moving through the workpiece material. That's what does the cutting, right? And so I got my cutting tool here. I've got some workpiece material here. So we've got our cutting tool here. And so it turns out if this is the velocity direction, so if the cutting tool is moving this way through the workpiece material, now what makes the cutting tool move through the workpiece material? What about the machine? Somebody's trying to say it. So it's the spinning of the spindle that makes the cutting tool move through the workpiece material at this scale. right? So at the macro scale, so we got a milling machine. Our milling tool is going like this through the workpiece material and it's making chips, right? Filling up a whole bucket with the chips. But the cutting is happening because of the rotation of the tool. The feed motion of the tool, all that's doing is putting it at a place where there is material to remove. All the cutting happens because of the rotation. All right, so this velocity is what then? Based on our talk about process variables. Well, when we do the science part of it, we like to keep it constant because dynamic is a pain to do the math. Right? So we'd like it to be constant because we're talking about science. But so that velocity going through there is the surface speed. What's the surface speed again?
The relative velocity between the material and the cutting edge of the tool.
Right, the relative velocity between the material and the cutting edge of the tool. How do we calculate surface speed? This was the whole proportional thing I tried to figure out yesterday on the thing, right? Right, so it's we have to know the diameter of the tool because we calculate the circumference of the tool if it's a milling cutter, right? And then so it's the straight line velocity, so the tangential velocity of the point on the x outside of the tool. What if the tool is coming straight down into the material and we care about the center of the tool? What's the surface speed at the center? 0. Surface speed on the outside edge equals pi times diameter times RPM. I don't know. I gotta make sure the units cancel. Hard for me to say that out loud and watch and visualize the units. We want to make sure the units cancel, right? We might have to divide something. We might have to add a 12 in there somewhere to go from feet to inches, right? So our surface speed is the velocity we're talking about there. So wouldn't it be cool if we could do experiments where we could understand what's happening? So here we got workpiece material. Here we have chip. Right, so we've seen workpiece material and we've seen chips, right? There's a whole bunch of science that has happened to understand what happens there. Because that's where it transitions from workpiece material to chip. And if you can make that more efficient, then you can put chips in the bucket faster, then you can make airplanes faster, then you can win the war. Or what do we want to win these days?
The lotto.
Powerball.
War on terror.
The war on terror. What do most manufacturers these days want to win?
Money.
Yeah. We want to win profits, right? Maybe we want to win all those profits because we have this thing we want to do with all the money we got. I plan to be rich because I want to spend all my money supporting manufacturing education programs. So that's why I want to be rich. But our manufacturing companies, they want to make profit, right? So we can understand this, and so this process, we said again, this is the most fundamental process in manufacturing today. It's responsible for the things that we have. So we're going to talk about this. So scientists measure things. What else do scientists do? They design experiments. They model things, right? So we're going to model the cutting process here. We might do some experiments where we understand the model better. All right, so we talked about things that we can measure, right? We talked about why engineers measure things. We talked about why scientists measure things. You guys passed everything down? Did you get one of these yet, Tim? You can go ahead and measure your dowel pin if you didn't yet. Pass your cards over there. What are the things we got to worry about when we do a measurement? Edward.
The uncertainty in the device you're using to measure.
The uncertainty in the device we're using to measure. We need to understand measurement uncertainty. What else? So, Travis. So the condition, yes. So if the device is in poor condition, it's likely to increase the uncertainty, right? Right. So we absolutely. So you guys, you did your calipers, you passed all the things back down. We're going to look at the results of your measurements tomorrow at the beginning of class. But since I've got everybody's attention, undivided attention here, I'd like to talk about measurement tool etiquette. Our measurement tool has a box. Our measurement tool is inside the box. It should be in the box or in our hand, but not on the table. So, if you feel the need to put down the measurement tool, put it back in the box. I mean, momentary instances of, okay. But you can't find these later when the box is over here and the caliper is over here. So that's a problem. So if you always put it back in the box, at least if you can't find it, you can't find any of it. Right? Another piece of advice for tools with boxes. Keep the lid of the box closed whenever you have the opportunity to keep the lid of the box closed. I had a summer job working in, anybody, some of you said you had been in a paper mill or seen a paper mill before. Anybody ever worked in a paper mill before? I had a summer job as a millwright. I think I was, by then, I was an apprentice millwright at the time. The millwright is the guy that sets up all the big machinery that makes the plant run, right? And so you have, so would you believe that all those 30-foot long rollers have to be aligned well when they're spinning at, I don't know how fast they spin, a couple thousand RPM? Yeah. If the alignment is off, bad things happen. So we had this $6,000 laser alignment tool that we used to align those things to make sure it was all lined up before you started the roll going. They have this stuff in paper mills called black liquor. The black liquor is like this tar-like substance that flows, kind of like molasses. You don't want to smell it. And it gets piped all around the mill. I can't remember what it's for, but it's, you don't want to deal with it. Sometimes the pipes break, and your box with your laser fills up with black liquor. Oopsie. So be careful with measurement tools, things like that. It certainly shortened the lifespan of it. All right, so we got measurement uncertainty. What's that?
I was like, and the black liquor shortens your life.
Yeah, it probably does if you're in the box too. Yeah, it's not good stuff. So we got measurement uncertainty. How do we better understand our measurement uncertainty? So we've got terms like calibration. What's calibrate mean? So to calibrate, as defined by the ISO, the International Standards Organization, is to compare with the known value, or compare with the true value, I think is the wording that they use. So to calibrate is to compare with something that we know. Uncertainty is so you can report the uncertainty of a calibration. So that tells you so what goes into uncertainty? So we all understand that the uncertainty of measurement is like when we look at the measurements that you had here, they're not all going to be the same number, right? Right. In fact, if you measured it 10 times, you probably didn't get the same number 10 times. Right. So that's our uncertainty in the measurement. What are the factors that go into uncertainty? Measurement uncertainty. Edward.
The precision of the instrument.
So how precisely the instrument. So what's the difference between accuracy and precision? Edward again.
Okay, so accuracy, so precision basically just has to do with the number of decimal points.
That's the way to say it.
just how much decimal points you can get into your answer, whereas accuracy is more like getting a consistently correct answer.
Okay, so I think I see where you're going. That's not how I would have described it. You had a different way to say it?
Accuracy
You have like 2 minutes
is,
left, right?
accuracy is how close the measurement is to the real thing, and precision is how consistent that measurement is.
Exactly. So when I'm talking about accuracy and precision, I'm saying, so our accuracy is how close to the true value are you? The precision is how close together are your measurements. So these are 2 factors in uncertainty, right? What impacts those kind of things? Temperature. What else? Oh, so you said one thing, how many decimal places, right? So I can always get a more precise measurement by decreasing the resolution of my measurement tool. If I use fewer decimal places, I will get higher precision, but maybe not better accuracy, right? So what goes in? So temperature, operator to operator variation, part to part variation, right? There are systemic problems, right? The operator always presses too hard, so he always gets a measurement that's too small. There are random problems or chaotic problems, we're going to call them. So these are problems that don't happen the same way every time. So we're talking about measurement, calibration, uncertainty. Okay. We will meet again. Oh, wait. Assignments. There's a group assignment. It's posted in the group assignments thing. You can't see it until you become a member of a group. I knew there was a flaw with my system. Let me read it to you. Now, so the group assignment is, I'll tell you to start with, and then I will send an email to the class to tell them what it is. Group assignment is, form a group with 4 people. Groups must have 4 people. No group with less than 3 people will be accepted. No group with more than 4 people will be accepted unless the math doesn't work. So I want groups of 4. We'll accept a group of 3 or a group of 5, depending on how many people are in the class, right? So by Friday, I want you guys to have created a group, had a group meeting, had a conversation with your group partners about 1 hour per week that you will be able to meet on a regular basis for the rest of the term. And all of you must add yourself to one of the group things in the MyWPI site, and I will show you with the click-by-click instructions how to do that in my email, so that you're a member of the group, and then for that group, then the group assignment will show up. Then you can log into the group assignment and you can post the results of your meeting. Okay? So this is worth 1 point on your final grade. So as we look at as you look at the grade book on Blackboard, if it says 5 points, that's 5 points out of 100 at the end. I try to have it so that all the things at the end of the class add up together to be 100. That's why your CAM assignment might be out of 1.2 points, right, or 1.5 points. That things to you. So at the end of the so there's 5 points. The syllabus says there's 5 points for doing the surveys. There will be 7 surveys. If you complete 5 of them, you get 5 points for your final grade. Let me give you a little hint. If you open the survey and close it without answering any of the questions, it gets marked as complete. This should not be a hardship to get those 5 points. Don't complain to me at the end of the term that you didn't know you had to do the surveys. I would like you to fill them out though, because they give me feedback about what's going on and what we're doing. The discussion forum has been clarified. I posted the wrong picture last night.
So how do we
Talk to people.
I'm not sure.
Another
Is it the cam part?
Is it just for one?
I clarified the problem in the discussion forum. I posted.
No, you know it was base bottom or whatever?
Right.
Yeah, we have to make that in CAD software with all the
I
contours.
posted the assignment for
I think that's
CAM 2-3
versus
and the
one.
assignment for CAM 2-1
Okay.
when somebody asked me about it.